Hello, hello. Welcome to Isaac Computer Science GCSE Livestream.
Welcome, everyone. This is live stream number 4. We're creating quite the franchise here.
An Isaac Expanded Universe. I like it. Very superhero.
Yes, I think we need to make it more epic, though. We need superpowers. What would yours be, Katie?
Well, my last name is Sparks and I'm a physicist, so I think I'm going for something electrical manipulation. How about you?
I think in this imaginary universe, I would like to be a villain. Maybe something like the Riddler, but rather than riddles, it could be encrypted messages. I could be called the Enigma.
Or the Enigmac.
Great work, great work. Now we have a franchise. Let us know in the comments if you have any more ideas for our Computer Science Superheroes series.
Speaking of computer science superheroes, this week we'll be joined once more by computer science educator and digital trustee, Julie Price.
Yes, Julie is back. Last week, Julie gave us an introduction to systems architecture, including a brief history of the computer and a look at its components, including the CPU and von Neumann architecture.
Yes, the eyeworm, which wasn't the only bug we encountered in the session. If you didn't get a chance to watch the session live, you can watch it back in our YouTube gallery.
Now, for some housekeeping, if you have any questions during the live stream, please feel free to share those in the chat or by using the question form below. We're going to leave that there for a little while so you've got plenty of time to open it up.
And at the end of the session, we will share an Isaac Computer Science game board featuring some questions from the platform for you to try so you can test out what you've learned today.
So let's bring on our expert guest speaker, Julie, and find out what she's got in store for us today.
Julie, welcome to the stream.
Thank you. It's lovely to be back.
It's fantastic to have you here.
There is one thing I would say, though. You both have your superhero powers. May I have some as well, please?
Absolutely. I feel like for you, maybe it should be something to do with like perfect recall of like historical facts or something. You shared so much good stuff from history last time.
Well, in fact, the area that I'm really, really interested in is cognitive neuroscience. So this is brain development. And so I was thinking something along those lines. For example, superhero powers would be something like super quick processing.
Yeah, or mind reading maybe.
I'm sorry?
Or mind reading maybe.
Well, yes. This is an application of theory of mind. Yes, so mind reading. So it's also it's that very quickness, the quickness, incisiveness, and being very rational. I'm always thinking like a superhero who's got Sherlock Holmes features.
Nice. Yeah, Sherlock is a bit like a superhero.
He is. He's also possibly got a little bit of kind of robot processing powers.
Yeah, there's lots of links there. There we go.
We're getting into artificial intelligence there.
Love that, Julie. So in your last session, you took us through some pretty fundamental concepts in computer architecture. You showed us that eyeworm. You taught us that the first computer bug was a real, literal bug. You gave us a lot of the history of the computer, how we got to where we are today. And we looked at some components like the main memory, RAM and ROM, and also those buses. So what have you got in store for us this week?
What I got in store for you this week is that we're going to focus on the processor, what it processes, how it processes, but something that's really important from my perspective, and I'm sure from others as well, is the interaction of those components.
That sounds fantastic, Julie. Take it away.
Right, I will do. Here we go. Now, again, welcome. And what we're going to do this week is to focus on the building upon what we already know. So as you see here, there's the eyeworm from last week, which shows the relationship and the communication channels between the different components. Now the arrow shows fetch, decode, execute. Now, this is the cycle which we're going to be exploring, which is the province of the central processing unit. Right, so focus for today, remember what we're going to look for is what is the processor. So just recapping on what the processor is, and then the what does it process, how does it process, but then those interactions. So we've seen the pathways between the main memory and the processor. We've seen the pathways between the input and the output devices in relation to what's being processed. But we're going to look closer down in at the processor today. So this is an image of an image which shows you part of that eyeworm. Now here what we've got is just the main memory over to the right, and over on the left we have the central processing unit. Now this image would have been shown as a block of pink and a block of the gold color, but we've peeled away that outer layer to look inside. Something else from that eyeworm is the black connectors that you can see on this diagram. So we've got the control bus, the address bus, and the data bus. Those are really important for what we're doing today. So let's just a little recap on the processor. So it's hardware. Remember we distinguished last week between hardware, software, liveware, hardware, touch and feel it. You've got the mechanical stuff there. And you have the software, which is the program, the instructions for the computer, and also the liveware, human beings. I have heard human beings called something else in relation to computer, which is not very complimentary. Now, what does this processor do? It carries out program instructions, and this was why I was really keen last week to share the development of the processor within computing for you, because you'll remember that it was only in the mid-20th century that the first computer which carried out program instructions was actually built and used. Now, as you see here, don't worry about focusing on the different components for the moment, but there are several important components, very important components, and each of these components has a specific role. What we'll do is we'll come back to that later on, actually having a look at each one specifically as just a signpost for your further studies. Now, the processor, how does the processor process instructions? So we're on to that second question now. This thing, the fetch, decode, execute cycle. There might be some of you who have gone through this so many times in school, with your own revision, etc. But there may be some of you for whom this is your first exposure to the fetch, decode, execute cycle. So what I'm going to do first of all is just to mention what lies behind these words. So I liken the fetch part of this to when you're out, maybe you have a pet dog. You throw the ball and say fetch to your dog. Your dog runs off, grabs hold of it with its teeth, and then brings it back to you, or whatever you want to do with it. So fetch is getting something. Decode, for example, you may want to communicate with somebody in your group at school, and so you send a piece of paper, perhaps. I'm sure you wouldn't do this. Happened many years ago, but I'm sure it doesn't happen now. But in such a way that it's only the person who receives it actually can decode it. So I liken it to a meaningful communication, actually deriving meaning from the communication. Now, execute. Now, we're not a history lesson here, thinking about the French Revolution, but execute as in getting the job done. So having said that, having unpicked those, so the fetch something, decode it, make it happen. So there is one concept which I would like to just linger on for a moment before we get into the cycle itself. Now, this is the clock. Now, why is there a clock? Now, the system clock, I'm going to read these out because I think there's value in doing it. The system clock generates a regular, now that's important, regular pulse by emitting a clock signal. So there's the signal, so there's a pulse. So you can just imagine a pulse, okay? Now, what does this do? It's used to synchronize. Now, if I just go through that word synchronize for the moment, synchronize is derived from Greek. And if you look at a translation of this, a literal translation of it is to occur at the same time. So it's used to synchronize the operations of the processor components. So they all have their job to do at a particular time, but they need to coordinate with each other. They need to synchronize within this time frame. Okay, now, as you can see from the diagram, now I'm going to linger on this diagram at the moment. So you can see that we have the y-axis that shows volts and the x-axis, which shows time in milliseconds. Remember, a millisecond is 1,000th of a second. So you can just imagine how short a period of time this is. What's happening here is that the clock is activated. So one clock period, if you have a look at the double arrow line here, the clock period extends from a rising edge to a falling edge, and that represents a cycle. So it's continuously switching. If you see that that's one clock cycle, but then it's repeated another clock cycle, it's repeated another clock cycle, it's repeated another clock cycle. So I'm not going to go into that in too much detail now, but I hope you can see that it's an image that upon which you can hang learning. One thing I would mention over that, though, is that volts, if you remember that this is a unit of electrical potential difference. So we're looking at continuously switching between low, high, low, high, low, high, etc. Now, the clock cycle is the time taken between two sequential rising edges. So if you see the rising edge, it's the clock cycle is the time taken from the beginning of one to the beginning of the next. Very, very important. One clock cycle is equated with one program instruction. So one program instruction happens within one clock cycle. And just for your just clarification, and just to give you a little bit of context here, is the measurement which we use, the SI unit, for clock cycles per second. So 1 hertz is 1 clock cycle per second, and then we have 1 megahertz, a million of those, 1 gigahertz, 1 billion of those. So when you have a look at the specification for your laptop or something, you'll be able to convert that and contextualize it. Now, we're getting onto the fetch-decode-execute cycle now. And before I start this, I must mention a caveat that this is a simplified version of something that's quite complex. And it is with practice, exposure to it, thinking about it, and actually engaging with what is happening, that this information, this knowledge can become yours that you can retrieve. But as just going through this, it will be insufficient for you to embed that knowledge. You need to embed it for yourself, with your teachers, and also at the Isaac website. So very, very briefly, if I just go back, we're familiar with that. What I'm going to do now is I'm only going to show the central processing unit. Now, the control unit down in the bottom right here, it places a read signal on the control bus. And please excuse the buses here. They're not actually buses. These are just connecting wires. in inverted commas. So they're connections, but some person thought about calling them buses. So the control unit, bottom right, sends a read signal on the control bus and the address of the next instruction data, and this is placed on the address bus. So two buses are involved at the moment, the control bus and the address bus. Now, these are sent to main memory. Main memory, we have not got on this illustration here, but you know it's over to the right. Now, this receives and places the instructional data on the data bus. So we've got all three of them involved now. When the main memory, I've put this in italics because we're thinking back to the main memory receiving the signals. So when the main memory receives the signals, it knows to read from that memory location. I won't repeat what I said last week about memory locations, but I would refer you back to that. Now, we're into the decode stage now. So the control unit, again, bottom right, a very, very important component in the fetch, decode, execute cycle. They all are, but this one, you'd be lost without it. Control unit, it decodes instructions which are in binary. And here we've got an 8-bit binary, in inverted commas, word, so that it knows what to tell the other central processing unit components to do. Now, I'll linger here just for a moment, but this is for you to look at for the future, that the two nibbles from which this is made are very, very important for knowing where and what to do with instructions. I'll leave it at that. Finally, into the execute. So instructions are carried out. So we've had the fetch, go get, the decode, what does it all mean and what do we have to do with it, and the execute, let's get it done. The instructions are carried out. For example, and I've only got two here for you. And this one relates to my superhero powers. If calculations, so add, subtract, multiply, divide, Boolean logic, so it could be and, or, not, or exclusive, or, etc. Or comparisons, less than, greater than, less than or equal to, greater than or equal to. If that's involved in the instructions, then the arithmetic and logic unit would be used. And you see that just above the control unit. Also, another example, any result from a calculation will be stored in the accumulator, which is above again in this illustration. And any result from a calculation will be stored here and used in another calculation, or it could be saved to main memory. Now, I mentioned earlier that I would focus on the main components, but this is something that I'm hoping that you're going to revisit. So we've got the program counter holds the address of next memory location, the memory address register. And as you see, I've included these in the order that they come on the diagram. So the memory address register. Now, this is a temporary storage of memory addresses. The memory data register is it temporarily holds data. The memory addresses, the memory data. The current instruction register, this holds the current instruction that the process is executing. And now onto the other side. I've switched the picture over to the other side. So we can see the accumulator, which I've already mentioned, stores the result of the calculation. The ALU, bless it, carries out arithmetic calculations, logical operations, and comparisons between values, which I've already mentioned. And the control unit. This is really rather important. It organizes the execution of the instructions. It manages, it carries things out. It's central. Where next then? So we've gone through the fetch, decode, execute cycle in a very, very condensed version. And I would say that when simplifying something, precision and exactness is the casualty. So I really do recommend your reading around this. So it's just a snapshot, and you really do need to know it in greater depth. A bit of a shout out here for Isaac. Obviously, Isaac's website will give you so much support in your learning, but I want to shout out the animations that you'll find of the fetch, decode, execute cycle. They are, in all the years that I've been encountering this, it's probably, I will say in my opinion, the best I have come across. So here we are, the Isaac website. It contains so many resources, and I've included the not to be missed animations, but there are more. There is so much to explore there. So where next with the processor? Now, I've gone back to the iWorm because this is something I'd like to share with you for you to actually engage with. So rhetorical questions at the moment. What is cache and how does it affect performance? And how is performance affected by the number of cores? What are cores? And then what other factors affect performance? A little bit of guidance here. For the cache, think of it in terms of main memory. So I would say go to the systems architecture content of the Isaac website, but I'd also recommend that you go to the memory and storage section as well, because that gives you far more information about the cache. The cores, you've probably come across this already. In my computer, I do believe I have 4 cores, but we show 2 here, but what is the core? What does it do? If you've got more than 1 core, what does this enable you to do? There is so much more that we could explore here, which we don't have the time to do. Some of you will be looking at the types of processor as well. And Isaac does actually have that on the website. It's not on every examining board curriculum, but you will find this, you will find information about the different types of processor and also thinking about the graphics as well. Right, with that, I'm going to pass back to Katie and Mac. Thank you very much for your attention, and I hope this has been useful to you.
Mac started off muted.
My bad, guys. Thank you so much, Julie. I love it when someone explains something to me, especially something so complicated as the fetch-decode-execute cycle, and I just get that moment of, I've got it. I've been inspired to go read more on the Isaac website.
Me too. That was brilliant, Julie. Thank you so much. We're going to move on to the Q&A section of the session. So if you have any questions, do let us know using the form or the chat below.
Absolutely. I had one question to start us off. Earlier, we've had a couple sessions from Alan about Boolean logic, and so I just wondered, what is the link between the Boolean logic gates that we saw and the arithmetic and logic unit, which sort of seem to do some similar things? So I wonder if there's like a link there that we can kind of share with our viewers.
Oh my goodness, I'm going to ask you to use your imagination. Imagine that you have a very, very strong microscope. So you put your, let's say your Raspberry Pi 4 underneath the microscope, and then you focus down in to the central processing unit. So all you can see is the central processing unit. And then if you dig down deeper, metaphorically speaking, so if you look down closer, so all the time you're panning down into the tiniest elements which you can see within the central processing unit, you will eventually, as you focus down deep, you will see the circuits. You will see the circuits actually there. You will see the adder, the half adder. You'll see each of those logic gates. But then as you pan back out again, you'll see it in the context. And this is, I have actually seen this happen, and it's, well, it's jaw-dropping how small everything is inside CPU.
Amazing. Thank you,
Oh,
Julie.
that's brilliant. How does it know what things to decode, or how to decode things?
That's a very general. Could you expand upon that question, please?
So in the fetch-decode-execute cycle, which when things get to decode, how does it know how to decode it?
Yeah, how does it know which instructions equal which code? Like, is there some list somewhere? Is it just all processors born knowing the instructions?
Maybe I can share this. I could go into an in-depth description of this. However, if I share something with you, I've got here. What I've got here is a diagram. What I'll do is I'll just point to the different parts. What I did when I came across the central processing unit, first of all, I thought this is very, very complex. And so what I need to do is I need to create a graphical representation of it. So over here, I've got the program counter, the memory address register, the memory data register. Down here is the control unit, all the different components. Over here, I've got the accumulator and the ALU, the arithmetic and logic unit, and also something that I haven't focused on too much here, which is the current instruction register. Now, getting back to the question, over here, we can see the main memory. Now, this has two columns, the address and the data. And this is, if I bring it in closer for you, you can see that we have a number of zeros and ones. Now, if I just pan out again and come back in, here we have what I call the, I think I've got it here, decode unit. Now, what we have, yes, that looks as though, can you see in the first column, we've got what's called the opcode and the operand. Now, this will tell the computer what to do and to what. And we've got down the side here, this is just a particular example which I use. We've got down here whether the computer needs to end what it's doing to add, subtract, store, load. And so it's part of this complex sequence, every single aspect of which is included, which means that sometimes you can infer things, but computers aren't like that. So everything needs to lead to everything else. There isn't any room for maneuver. It's all logically and rationally out, organized, sequenced.
Amazing.
I don't know if that directly, I'm not quite sure of the question. I'm a little unsure of the intent of the question.
I think that was perfect. That was perfect, okay. Julie. It does have a list somewhere in the decode unit. It knows what the instructions are. So thank you.
That was a really useful learning tool. That's about all we've got time for, folks. Brilliant questions, everybody. Julie, thank you so much for answering those questions and sharing that fantastic map. I've learned so much in the last 2 weeks.
It's been a really interesting session, and your last one with us, Julie. Thank you so much for joining us. Thank you, thank you, thank you.
Thank you for inviting me.
All right, we'll see you later, Julie.
If you want to test yourself on everything you've learned today, we've put together some questions for you to have a go at. You'll find them by typing the short link below in your web browser.
Yes, and don't worry if you find any of the questions tricky. We've got loads of hints to help you find the right answer, and all of our materials are mapped to the exam board specifications for AQA, OCR, EdXL, Educast, WJC, in order to make them directly relevant to your GCSE studies.
We've got a bit of a break before our next session. If you've missed any this half term, you can rewatch the recorded sessions on YouTube. We'll be back after half term on Wednesday, 2nd of November, where we'll be joined by computer science expert Melanie Denig.
Yes, join us then for a session on sequence, selection, and iteration. It's the first of 3 sessions on programming concepts.
Let us know how you found today's session by filling out the feedback form below. You can also let us know if you have any suggestions or topics that you would like us to cover. Thank you so much for joining us, everyone. We'll see you next time.
Absolutely. Thank you, everyone. See ya.